Hello everyone and welcome back to Exam Ignite YouTube channel. This is 5th semester's digital communication subject code BEC503 module 5 video where we will be studying about the convolution codes. In this, the first part is convolution encoder, then we have the code tree, then we have the Trellis graph, and along with that we need to know the state graph, then recursive systematic convolution codes. That theory part had been asked in the last year paper. Then optimum decoding of the convolution codes, that was also asked in the June-July 2025 paper. Then comes the maximum likelihood decoding of the convolution codes, where we have the Viterbi algorithm, where you in the model question paper they have asked the step-by-step procedure of this algorithm, and the examples of that we will be studying now. So moving on to the syllabus here. Firstly, convolution code. In a convolution code, it is a block of n codes that digits generated by an encoder in a unit time of t and not depends on the block key. So message digital bits also preceding m-1 block. So explaining the theory part, the message block, we are having the convolution encoder and where it gives out the code blocks and at the code rate of k by n. So in general, you can say the convolution encoder is given by n comma k comma n. So everywhere in the questions that you will be getting in the numericals will be in the format of this, where the first one is about the n is a number of modulo adders that are being used in the problem, and k is the number of bits entering the encoder, that is the input that we are giving, and m is the number of flip-flops that are being used. So l, another one, it is the number of digits in the message sequence. These are all the notations you have to know. So the code rate of the convolution encoder, it is given by k by n. So there are two ways to generate the convolution code. One is the time domain approach and another one is a frequency domain approach. In the time domain approach here, we are given the impulse response is given by G1 and G2 till Gn as like this. So here the impulse response from the adders can be interleaved or arranged in the form of matrix with L rows and L into n plus 1 columns. Such a matrix is known as the generator matrix of the convolution code. So coming to the directly the problem, let's start with the first one, where it is given as for a 2 comma 1 comma 1. So here n is 2, our k is 1 and our m is 2. It is a convolution encoder in the shown figure. We need to find the output of the encoder using the time domain approach. They have specified here for the message bits that been given. So first, what message bit this is going as input to the encoder. And here we are having, as they have mentioned, number of flip-flops is what? There are 2 flip-flops and there are 2 output points. This is the output, and we are having 2 adders along with 1 input. So input is given 2 flip-flops, and it is showing that 3 lines are in the upper part, and in the lower part only the 2 inputs, and totally we are getting the output to the channel. So moving on from the diagram, you can say we are having, as I said, explained it. Now how to write the impulse response? You have to write it on your own a few times. It may not be mentioned in the question. So for this, how you have to write is, this is the input that a modular is getting. Like you can say, this is the first input that is the modular is getting. This is the second one, and this is the third one. This is the upper part where we will be giving the g of 1, and in the lower part we will be getting the g of 2. So it is for the g of 1, it is 3. All the 3 inputs are there, so you can write it as 1, 1 and 1. And for the output part, you can say, so from the input we are getting the 1 input to this modulo, and here it is 0, and next here it is 1. So hence it is 1, 0, 1. So length is what? Length is calculated by this formula, and we got it as 14. Now you need to draw the generator matrix. So the generator matrix has mentioned, you need to first count the matrix size. So to count the matrix size, it is L into N of L plus M. So on calculating that, we get it is 5 cross 14 is the size of the generator matrix. So how do you write that? So you can observe that here in the G1 and G2, here in the G1 you are first taking 1 and taking the 1 of this G2 and writing it as 1, 1. And nextly, consider this one and this 0 and write it as 1 0. And next, consider this one and this one and write it as 1 1. So next, you have to make how many times it has to get repeated is 1 2. So here you can observe how many columns are there. Here we are having 14 columns, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So for the 14 columns, remaining parts will be the 0. In the remaining places you have to put 0. Next is what you have to shift 1 0 to here and continue this sequence. Again this goes here and this goes to the next place and this goes to the last. So this is how we create our generate matrix. So then we know the equation C is equal to D into G. So D into G, how to write that? D is the code that has been given in the question and G is the generated matrix that we have found out. Now multiply it like multiply it the each row with the each column. Each one you have to multiply. This should get multiplied to this first row as well as to the this first row as well as to the second row. And then like this you have to multiply for all the 14 columns. After multiplying to the 14 columns, you will end up with the final output. Now you can observe this is the final code that we had needed. Moving on to the next question, this is 213. So here our n is 2, our k is 1 and our m is 3. This is the convolution encoder. So find the output of the encoder using the time domain approach using the bits they have given as this. So here you can observe what is the G1 you have to write. You have to write it as 1 and here it is 0, 1, 0, 1. So you can observe it is 1 and here you can observe it is 0 and from the flip-flop 2 it is going as 1 and it is 1. Coming to the G2, how much we are getting? We are getting the 4 inputs here. So it is 1, 1, 1, 1. This is our C1 has our output and C2 has our output. Now calculate the generator matrix size and based on this G1 and G2 you have to write the generator matrix as I said before. After that, as usual, C is equal to D into G and D is given and G is what we have generated. We get the output. Now moving on to the frequency domain approach. Here the procedure is to find the convolution code in the frequency domain approach is as shown. Firstly, you have to, for the j number of modulo 2 adders, the generator polynomial is given by this. Now the output of the 2 modular, it is given by C of x and the output of the encoder, it is given as C of x. Let us consider one problem. Here in the problem, it is given as n is equal to 2 and k is equal to 1 and m is equal to 2. The convolution encoder is given. You need to find the output for this message using the frequency domain approach. So write G1. What is G1? It is one input, second input and a third input. So 1 1 1. And for this it is what? It is 1 0 1. Now you have to convert it into the X format. This is how you do for the 1 1 1. It is as we did in the fourth module, you have to write 1 as 1 and 1 as x and the coefficient of next is x square. So there is no 0, it is continued. Here actual what happens is 1 plus 0x plus 1x square. So this is 0. So finally you get it as 1 plus x square. Now as usual, we know this formula C is equal to D into G where D is given as the equation that we had got. Let me write that 1 0 0 1 1 that we had it's written here 1 0 0 1 1. So here also it is 1 plus 0x plus 0x square plus x cube plus x power 4. So here this is 0 and this is 0. The remaining one will be my d of x. So write down the d of x and first find it out for g1 of x. You multiply it with each term and then finally you will get the first one c1 of x. So next is similarly for the c2 of x, write down the d of x into g of x, you will get the value. So finally the value of n is 2, so x power n is x square. Here we are finding out 2 c1 and the c2, so our n value is 2. Then we have to multiply c1 and c2x with the x square. So on multiplying that with the x, we should multiply the power of x to that. To this we have to multiply square. So what it will become is, for the each of the equation for this equations as well as for this equations, you have to multiply it by x square and you will get. The final our equation is c of x is given by c dash of x square plus x into c square of x square. In case if you are having one more term, that is n is equal to 3, then you will be having x square c cube of x square, like that you will be having. So if depending upon the size of the n, this varies. So next, moving on to that substitution part, substitute each of them, multiply x to whole term and you will get this expression. Finally you have to change it to the binary format. So now group the binary into the 2 bits and we have the 2 adders. So 2 adders. So finally this is what the C that we have got. Multiply to find out the G matrix, and if you multiply it, you will get the same answer. So this verifies that both in the frequency domain as well as in the time domain, we will be getting the same answer. So another one problem we are having where it is 2 comma 1 comma 3. You need to do using the frequency domain approach. What is my G1? It is 1 0 1 1 and it is 1 1 1 1 is G2. So finally using that, you will find out the c dash of c1 of x and c2 of x and finally c of x. And using the frequency domain, you can verify that you have using the time domain, you can verify it. And the next one is 2 comma 1 comma 4. The output is given in the frequency domain. Here you can observe we are having 4 flip-flops and we are having 4 here. The first one goes here, so it is 1 and 1 2 3 4 5. So we have to give 5 inputs here. And for the next is 1 is missing, so the another part is actually here, another one has to go. This is for the G1 and this is for the G2. So hence now it is correct, G1 and G2, and my L is equal to the sum of all these three. Find out the sum of L n of L plus m is equal to this. Using this formula, you will find out the value of n as 18. And then we will get the generator matrix size. Using the generator matrix size and G1 and G2, construct this in the time domain approach, and you will get it in the frequency domain approach. If you have to get it in the variable form in the algebra equation, then C of x, C1 of x, then C2 of x. Finally, you will be getting the C of x and convert it into the binary format. So next comes the most important part, that is state table, state transition table, and code tree. State draw, all these things are important. So for a convolutional encoder, let me go to this problem in a different approach. So the question asked here is, you have to consider a conventional encoder of 2 comma 1 comma 2 with the G1 they have specified as 1 comma 1 comma 1 and G2 they have specified as 101. So the information sequence is given as the 10011. You need to find the output of the sequence using the time domain as well as the transfer domain approach. Let us go to that. Here you can observe, firstly that it is given as this is the message that we are input that is given. So based on this itself, we have to draw this diagram. You can observe the first one is number of outputs. Number of outputs is what? We are having 2 outputs. Write down as 2 outputs. Then what are the number of inputs that we are giving? Input is 1. Number of flip-flops we are using is 2 flip-flops. After writing this, now you have to match it up. So based on the G1 and G2 equations that are given, 111 and 101. So they have given 111 and 101. So 111 means from all the inputs we are getting the input to the modulo 2, and here we are getting from G1 and from the G3 and not from this. So let's move on. In the time domain approach, the matrix method, it is known as matrix method, the top adder above, what are they? That is what we have considered. In the bottom adder, this is what we have considered. So the generator matrix order is given by this formula. From this, we can know the generator matrix size. So based on this, using the G1 and G2, again here 1 1, first part will be 1 1, then 1 1 1, then 1 0, then 1 1. So go like this, you will get the first 6 part, then that has to be continued to here, 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 and finally here. So you got the generated matrix. Now using the given D and the generated matrix, multiply it to each of the row, you will get the result as C is equal to this as a output. Now transfer domain approach, let's see and check whether we are getting the same answer or not. Here this is the D that we had given. So write down their coefficients. So where the 1 is there, it is for x0, x3 and x4. So that forms our D of x. Similarly, for g1 of x and for the g2 of x, write down the two equations. The output of the polynomial is addressed from the obtained polynomial, as this is the equation, the general equation what we are having. So for this, d of x and g1 of x multiplied, and instead of taking common out that we had done in the last module, you can directly cancel it out, which are having the same powers cancels out, and the remaining one forms the C1 of x, and the C2 of x also samely. And from as the encoder is having equation with n is equal to 2, we are having this as our equation. On substituting this and multiplying the x to that, we are getting the same output. Next is state table. In the state table, the first thing you have to do is 2 power m. 2 power m is given as 2 power 2, where our m is 2 in the given question. So it is 4. So for the 4 state conditions are there. One is S0, another one is S1, S2 and S3. The binary description for each of them is 0, 0, 0, 1. Sorry, 1, 0, 0, 1 and 1, 1. Now comes the state transition table. So here you have to write down these table very clearly. First should be the present state, and next directly write the next state. Next, what present state's binary representation, then next state's binary representation. Then mainly we have to give the input to our encoder, and we will get the output. So middle you have to write down these expressions as dl, dl minus 1, dl minus 2. So present state here, it consists of S0, S1, S2 and S3 as I had given in the state table. Now next, what representation? It is represented as in the state table, only was represented like this. Now input each of them, we are giving 0, 1, 0, 1, 0, 1 and 0, 1. So what the conditions in the next state, it will be S0, S1, S2, S3, S0, S1, S2, S3. Now here binary representation of this, as usual, has how we write the binary code. Right here 2 zeros and 2 1, then 2 zeros, 2 1. Here it is 0 1, 0 1, 0 1 and 0 1. Finally, in the DL minus 1, DL minus 2, write down the in the format of reverse of the what we are writing the regular binary code for the 0, 1, 2. So like that you have to write for this 4 zeros, 4, 1, 2 zeros, 2, 1, 0, 1, 0, 1, 0, 1, 0, 1. And for this, how to calculate the C1 of C1 and C2. So basically you need to get the equation. How do we get this equation? It is by looking into the encoder. So you can observe here for the C1 we are having 3 inputs. So in the 3 inputs, the first one is DL, DL minus 1 and DL minus 2. For this, for the C2 it is DL and DL minus 2. So we got the 2 equations. So using this equation, you need to find out this C1 and this C2 with the help of these 3. Adding those 3 and getting the values. So this completes the table. So now how to write the state diagram. So let us see how to write the state diagram.